In this video, we are going to discuss about conductive fibers. As the name suggests, conductive fibers, we are using a polymer-based electrochromic fabrics, which shows promising applications in new intelligent displays, flexible smart wearables, and military camouflage. Thanks to their flexibility, lightweight, high degree of controllability, and wide range of color change. The textile structures which can conduct electricity are called conductive textiles. It may be either made using conductive fibers or by depositing conductive layers onto non-conductive textiles. A conductive fabric can conduct electricity and made with metal strands woven into the construction of the textiles. It can be inhibited the static charges generated on fabric to avoid uncomfortable feeling and electrical shock also. Methods of producing conductive textiles are summarized as follows. First one, adding carbon or metals in different forms such as wires, fibers, or particles. Using inherently conductive polymers, coating with conductive substance. Types of conductive textiles. Generally, four kinds of conductive textiles as follows. One is anti-static textiles, EM shielding textiles, E-textiles, functional coatings. In that, we are going to discuss about anti-static textiles. Static electricity can the buildup of electric charge on the surface of objects, which can be caused many problems for textile materials manufacturing and handling the product. In dry textile process, fibers and fabrics can tend to generate electrostatic charges from friction. When fibers and fabrics are moving at high speed on different surfaces like conveyor belt, transport bands, driving cars, etc., causing fibers and yarns to repel each other. These static charges can be produced electrical shocks and cause the ignition of flammable substances. Two techniques are known to prevent static electricity in textiles. One is to create a conductive surface and another is to produce a hydrophilic surface. Next one, EM shielding. Electromagnetic shielding is a process of restricting the diffusion of electromagnetic fields into a space. In this process, electrically or magnetically conductive barriers is used. Shielding is common technique for protecting electrical equipments and human beings from the radiating electromagnetic fields. These barriers can be rigid or flexible. When an EM beam passes through an object, the electromagnetic beam interacts with the molecule of the object, and these interaction may take place as absorption, reflection, polarization, refraction, diffraction through the object. EM shielding textiles material can be found in the form of knitted, woven and non-woven fabric also. The major component of these fabrics are fibers and yarns. To achieve an effective shielding behavior, these fibers should be electrically conductive. Conductive yarns can be made by blending conductive fibers with conventional staple fibers, twisting conductive or insulator filament together. For example, conductive metallic yarn such as silver, copper, etc. can be wrapped with insulating textile materials to create hybrid yarns, which could be integrated into woven or knitted structures. Hybrid yarns or metallic fibers can be integrated into these designs as what? Electromagnetic shielding effectiveness of the fabric decreased with the increases in fabric openness. E-textiles. Electrically conductive fibers and yarns have attracted great interest because of their distinguished features including reasonable electrical conductivity, flexibility, electrostatic discharge and EM interference protection. Conductive textile fibers are the primary component for wearable smart textiles introduced particularly for different applications such as sensor, electromagnetic interference shielding, electrostatic discharge and data transfer in clothing. Therefore, the demand for electrically conductive fibers and yarns is overgrowing. The development of novel conductive fibers becomes crucial with technological improvement in wearable electronics such as wearable displays, solar cells, actuators, data managing devices and biomedical sensors. E-textiles plays a crucial role in selecting the conductivity of smart textile electronics. Textile applications such as lighting, considerable current is necessary and low ohmic fibers are preferred. On other hand, for certain sensing or heating applications, lower conductivity would work better. So, it requires fibers exhibiting low electrical conductivity. E-textiles need flexible and mechanically stable conducting material to ensure electronic capabilities in apparels. Functional coating. For many applications, functional coating is a material interface and surfaces that provide beneficial functionality over their intrinsic bulk characteristics. Hence, coating provides a versatile method of modifying textile with conductive property. Subsequently, the textile fabrics act as a supporting structures or carrier material for the conductive finish. Conventional methods such as dip coating or roll coating are typically used to apply bulk coating in the form of a saturation or lamination that covers the entire surface of the textiles. However, as will be presented herein, the advent of nanotechnology in textile research, the development of novel process techniques, and the advancement of inks and coating formations affords the opportunity to apply coating to increasingly finer structures. The physical properties of this devices is low weight, high strength, flexibility, durability, elasticity, heat insulation, water absorbency, dyeability, drap, and soft handling.